Installing a conventional central air conditioning setup forces most homeowners to spend somewhere between $11,000 and $14,000 at the very beginning. After that comes an endless stream of electric bills and costly repairs year after year. Across many developing nations, however, even owning such a system remains completely out of reach. That harsh reality pushed one American chemist toward a mission that would consume much of his life. He wanted to create a method capable of warming and cooling an entire house by relying only on nature itself. What emerged from that pursuit was astonishing. The concept Harold Hay introduced looked nothing like the systems people were used to seeing. He described it as the most affordable and efficient thermal storage solution ever created for residential buildings. Tests reportedly demonstrated that the design could satisfy a home's heating and cooling demands throughout the entire year, without motors, without batteries, and without consuming even 1 watt of electricity. The obvious question became unavoidable. What exactly was this technology? Why did it function so effectively? And why do some believe systems like this would never be widely accepted in the United States? To understand Hay's breakthrough, you first have to realize the idea itself was not entirely new. Its roots stretch deep into humanity's past, connecting ancient survival techniques to modern engineering principles. Long before electrical grids existed, civilizations in Mesopotamia and throughout the American Southwest already understood something critical. The greatest weapon against extreme temperatures was not machinery, it was thermal mass. Massive walls built from earth and stone absorbed heat during daylight hours, slowly releasing that stored energy later. Yet those ancient methods still faced one major limitation. Solid materials transferred heat far too slowly. The forgotten secret behind true temperature management involved turning water into a controllable thermal battery. That ancient principle eventually became known as the roof pond system. One of the earliest ancestors of the modern roof pond could be found in ancient Persia with the remarkable yaksha structures. Around 400 BC, Persian engineers discovered how to make and preserve ice directly in the middle of the desert. Their approach relied on shallow pools protected by towering walls positioned along the east, south, and west sides. Those barriers blocked solar radiation while calming surrounding airflow. As a result, water could release its heat through long-wave radiation into the cold emptiness of the night sky. The effectiveness of the yaksha depended on a profound understanding of radiative cooling. Even when surrounding air temperatures stayed slightly above freezing, the exchange of thermal energy between the water and the clear nighttime sky could still generate ice. Ancient Persian builders had learned that the night sky behaved like an enormous heat sink. Centuries later, that same scientific principle would become the foundation for Harold Hay's revolutionary work. In 1952, Hay arrived in India during a post-war development assignment. What he encountered there was a disaster unfolding inside ordinary homes. Traditional roofs made from mud and thatch had been steadily replaced with asbestos cement sheets promoted as modern construction materials. The new roofs lasted longer, but they offered almost no insulation. During daylight hours, houses became unbearable furnaces. At night, temperatures crashed, transforming interiors into freezing chambers. Families who could not afford heaters or electric fans suffered the most. Hay recognized something disturbing. Industrial modernization had sacrificed human comfort in exchange for cheap mass production and profit margins. Determined to solve the problem using affordable materials, he spent nearly 2 decades traveling between India and the deserts of Latin America. There, he relentlessly experimented with methods for controlling building temperatures naturally. During those years of testing, Hay became fascinated by the combination of movable insulation and water's extraordinary thermal properties. By the 1960s, his ideas had evolved into what he called the Skytherm system. This refined passive climate technology used water's high specific heat capacity alongside adjustable insulation layers to stabilize indoor temperatures. In 1966 and 1967, Hay carried out early experiments in Arizona using water basins measuring 2 foot square and 7 inch deep. During daytime hours, the basins remained protected beneath horizontal insulation. At night, the water was exposed directly to the sky. The outcome was remarkable. His studies suggested that 6 inches of water could store enough thermal energy to provide year-round climate control for a home. After experimenting with multiple names for the invention, Hay finally settled on what became known as the roof pond system. The unusual tests conducted in Tempe eventually attracted the attention of Jonathan Yellett, a highly respected engineer in passive solar design. Because Yellett believed strongly in the concept, Hay gained the opportunity to test the full-scale system inside an experimental structure built in the Sonoran Desert. But before understanding why that experiment mattered, it is necessary to completely rethink what a roof actually is. Most people see a roof as nothing more than a protective barrier. A roof pond house operates differently. In this design, there is no traditional attic separating the interior from the outside world. Instead, the ceiling itself is constructed from dense conductive materials such as concrete or steel. Directly above that ceiling sit large industrial plastic bladders filled with several inches of water. That water becomes the heart of the system. It functions as a giant thermal battery capable of storing immense quantities of heat energy. Everything depends on a physical phenomenon known as nocturnal radiation. Any warm object located on Earth naturally releases heat toward the extreme cold of outer space. On clear nights, the universe effectively behaves like an endless thermal vacuum pulling energy away from the planet. The roof pond system was engineered specifically to exploit that process as efficiently as possible. When summer arrives, the entire cycle begins before sunrise ever touches the roof. Thick insulated panels powered by motors glide into place across the water-filled bladders, completely separating them from the open sky. As daylight intensifies and the roof absorbs the force of the sun, those reflective barriers bounce much of the incoming radiation away through the albedo effect, drastically reducing how much heat can penetrate into the water beneath them. Inside the structure, however, something entirely different is happening. Because the water containers sit directly against a conductive metal ceiling, they begin absorbing the warmth rising from the living space below. Instead of allowing heat to build inside the rooms, the water pulls that energy inward and stores it. Throughout the day, the house gradually becomes cooler while the water itself slowly heats up. Then night falls. Once the sun disappears, the insulated covers retract and expose the warmed water directly to the darkness above. Without solar radiation pressing heat downward anymore, the stored thermal energy starts escaping upward into the freezing emptiness of space. Hour after hour, the roof pond releases accumulated heat through nocturnal radiation. By the time dawn returns, the water is cooled back down again, ready to repeat the entire process from the beginning as the panels close once more. Winter transforms the sequence into its exact opposite. During daylight hours, the insulation remains open so sunlight can directly warm the water. As evening arrives, the insulated covers slide shut, trapping the collected heat inside the system. That warmth then radiates downward through the metal ceiling into the rooms below, heating the home naturally throughout the night. No furnace ignites. No vents force air through ducts. The entire operation functions silently, driven only by the endless movement of energy between Earth and the cold reaches of the universe. What makes roof pond technology remarkable is that its performance does not exist merely as a theory. Decades of measurements gathered by some of the most respected engineering and architectural institutions in the United States have repeatedly validated its effectiveness. The most famous demonstration came from Harold Hayes' Skitham House, located in the Sonoran Desert. The project received extensive monitoring from California Polytechnic State University, while part of the funding came through the U.S. Department of Housing and Urban Development. Researchers tracked temperature fluctuations inside the building for more than a year, documenting every shift in performance. The results stunned observers. Throughout summer periods where outdoor temperatures climbed to 100 degrees, interior conditions inside the house stayed between 66 and 74 degrees without relying on a single watt of mechanical air conditioning. During winter, while temperatures outside fell into the 30s, the interior remained near a comfortable 70 degrees using only solar heat previously stored in the water system. Those findings demonstrated something extraordinary. In a Mediterranean climate, a correctly engineered roof pond could theoretically handle 100% of a home's heating and cooling requirements entirely on its own. The idea was not limited to houses either. Studies published through the Passive Solar Journal alongside research from the American Solar Energy Society explored how roof pond systems might stabilize temperatures inside factories and enormous warehouses, where cooling expenses often become one of the largest operational costs. In industrial settings, the technology addresses a far more dangerous issue tied directly to national power infrastructure. Every afternoon around 2 o'clock, countless conventional air conditioners activate simultaneously. That sudden surge places enormous stress on electrical grids, creating brownouts and forcing utilities to fire up inefficient peak power plants that consume dirty fuels at extremely high cost. Roof ponds operate differently. Instead of demanding massive energy during the hottest part of the day, they discharge stored heat during nighttime hours when electrical demand is low. That shift changes everything. By moving cooling activity away from peak periods, roof pond systems create a pathway toward a more stable and resilient power grid capable of enduring the escalating heat waves of the modern age. The technology does not only benefit homeowners, it also eases pressure on the entire electrical network itself. So why are these systems still so rare? The answer lies inside a brutal economic reality known as the split incentive problem. Like many passive building technologies, roof ponds create little motivation for developers focused on maximizing short-term profits. Builders want construction costs kept as low as possible because cheaper homes produce higher returns at the moment of sale. A roof pond house, however, demands far stronger structural support than ordinary residential construction. A standard timber roof is generally engineered to support roughly 40 pounds per square foot. A roof pond structure must withstand nearly twice that load because of the tremendous weight created by the stored water above the ceiling. That means additional concrete, heavier reinforcement, and more steel throughout the building. For developers, the math becomes simple. Instead of investing in expensive structural upgrades, they can install lightweight air conditioning equipment for a fraction of the upfront price. The long-term burden then shifts directly onto homeowners through massive electricity costs and future maintenance expenses. But the conflict runs even deeper than construction economics. A roof pond is largely permanent infrastructure. Once installed, there is very little left to sell afterward. There are no complex compressors waiting to fail, no refrigerants leaking from sealed systems, no advanced electronic boards requiring licensed technicians for constant servicing and replacement. For industries built around recurring maintenance contracts and planned equipment failures, passive thermal systems represent a financial dead end. Over time, entire regulatory structures evolved around the opposite model. Building codes became heavily tailored toward lightweight homes dependent on energy-intensive climate systems. Securing permits for a conventional house equipped with standard air conditioning is relatively straightforward. Attempting approval for a massive gravity-loaded thermal structure, however, often becomes slow, expensive, and incredibly difficult. Another obstacle standing in the way of roof pond adoption comes from bureaucracy itself. Most regional building departments simply lack engineers trained to properly evaluate a roof integrated with stored water. Because of that, approval processes often become nightmares filled with delays, endless paperwork, and expensive custom calculations. For many people interested in building such a system, the additional engineering costs alone are enough to kill the project before construction even begins. As a result, notice society continues relying on energy-hungry climate machines, not because they represent the best solution, but because the modern construction industry has been optimized around selling products that are inexpensive, upfront, and easy to market to consumers. Convenience wins. Long-term efficiency loses. Still, Harold Hayes' roof pond concept was not without flaws, and those limitations deserve attention. During prototype testing, the movable insulation assemblies frequently experienced failures. Imperfect seals around the sliding insulation edges created serious thermal leakage problems that reduced overall efficiency. Water intrusion also remained a constant concern throughout development. Although, with a properly designed low-slope roof, those risks could be controlled far more effectively. For anyone serious about moving from theory into actual construction, one truth must be understood immediately. The design options available depend entirely on the structural capability of the building itself. Since the entire system revolves around the thermal mass of water, there are essentially three realistic ways to implement the concept, ranging from simple interior modifications all the way to a fully engineered custom home. The easiest entry point is known as the interior thermal barrel approach. This method requires no reinforcement to the structure and can be added inside almost any existing room containing a south-facing window. The setup is simple. Several large, dark-colored barrels filled with water are positioned directly where sunlight can strike them. In this arrangement, ordinary curtains, blinds, or window coverings effectively become the movable insulation system. During summer months, the curtains stay closed throughout the daytime hours to prevent direct sunlight from heating the barrels. At night, both the window and curtains are opened, allowing the thermal energy absorbed from the room to radiate outward toward the cool night sky. Winter operation reverses the sequence completely. Daylight is allowed through the window so the barrels can collect solar warmth. After sunset, the curtains close again, trapping that heat indoors while the barrels slowly radiate warmth back into the room for many hours afterward. This represents the most basic implementation path. Technically, it is not a true roof pond system, yet it operates according to the same thermal principles. For people seeking something more permanent, the next stage becomes the experimental retrofit approach. This configuration works especially well for off-grid workshops or remote cabins. A simplified roof pond can be installed using durable construction materials specifically designed to survive long-term exposure. Around the edge of the roof, a raised perimeter curb measuring between 6-inch and 12-inch should be constructed. Inside that containment area, installers place a heavy-duty EPDM pond liner rated at either 45 mil or 60 mil thickness. Unlike thinner waterproof materials, EPDM was engineered specifically for permanent water exposure and constant ultraviolet radiation. Rather than using a fully open pond, individual water bladders are usually preferred because they reduce evaporation while also minimizing dangerous water movement during seismic activity. Professional systems commonly rely on UV-resistant polyethylene storage bags, often marketed under the name pillow tanks. Some off-grid builders searching for cheaper alternatives instead use black polypipe systems or modified IBC totes. However, those substitutions cannot provide the same level of surface contact area found in a genuine thermopond design. For the movable insulation layer, rigid polyurethane foam or XPS panels represent practical choices. Most builds use insulation values ranging from R15 to R30, mounted inside treated wood or aluminum framing. These assemblies can then slide along heavy-duty track systems, similar to barn doors. In remote applications, a rope and pulley arrangement remains the most dependable solution because it requires no complicated electronics. However, automation can still be achieved through a simple 12-volt actuator powered by a single 100W solar panel connected to a small battery. Safety features also matter enormously. Overflow scuppers should always be installed precisely at the maximum fill level. If the pond depth reaches 10 inch, the overflow opening should sit at 11 inch. That extra margin prevents heavy rainfall from overtopping the perimeter walls and adding dangerous excess weight onto the structure. This retrofit method can also work on buildings already designed with strong flat roofs, including industrial workshops and shipping container homes. Ironically, one of the most difficult engineering challenges is not the water system itself. It is designing a reliable framework capable of moving the rigid insulation panels smoothly across the roof surface. The third and most powerful solution is the fully integrated load-bearing home. This approach requires an entirely new structure engineered specifically around the immense mass created by a complete roof pond system. Reinforced concrete or heavy structural steel becomes mandatory. In this configuration, the roof serves two purposes simultaneously. It functions both as the interior ceiling and as the floor supporting the pond above, creating a direct, uninterrupted thermal bridge. The physics behind the idea are actually straightforward. The real enemies are always weight and water leakage. Water weighs approximately 62 pounds per cubic foot. Even a relatively shallow pond introduces more than 30 pounds of permanent dead load onto every square foot of roofing surface. Whether using tanks, bladders, or contained reservoirs, structural calculations must account for that massive force, while waterproofing systems must meet approved flat roof standards without compromise. Yet for those willing to overcome these challenges, the payoff can last a lifetime. By harnessing the thermal mass of water together with the laws of nocturnal radiation, homeowners can remove dependence on grid-powered climate systems and replace them with a permanent structural energy battery that costs virtually nothing to operate. The larger goal goes beyond lowering utility bills. It is about breaking dependence on profit-driven utility corporations and giving ordinary people a path toward genuine energy independence. And perhaps that is why ideas like the roof pond remain so powerful. If you enjoyed this story and want to explore more passive cooling systems capable of transforming modern buildings, then continue following along for the next deep dive into solar chimney technology and the future of self-sustaining architecture. Thanks for watching. See you in the next one.